The next talk by Dr. Jeff Fraser will highlight how we use such data to uncover buried geology and open up new regions for exploration using the Tennant Creek to Mount Isa region as a case study. Jeff is the director of the Geochronology and Stratigraphy section and co-leader of the Australia's Resources Framework project within the Exploring for the Future program. Jeff has a Bachelor of Science with honours in Geology from the University of Adelaide and a PhD from the Australian National University. He has been at Geoscience Australia for over 20 years, where he has worked across a variety of Australian terrains, applying geochronology to unravel the geology and mineral systems history of the continent.
Hello everyone, I'm Jeff Fraser, and in this presentation I plan to present two case studies that we regard as successful demonstrations of how government geoscience programs have opened up new exploration search space for both minerals and energy resources. Before launching into the two case studies, I want to provide just a little bit of context for this work. In Australia, there's been a perception that some of the big resource prizes have already been found and that further exploration is too difficult or too risky. And one of the major impediments to resource exploration in Australia has been what has been called the cover challenge. Approximately 80% of the Australian continent is covered by a veneer of desert sands or deep weathering or variably deep Mesozoic or Cenozoic sedimentary basins, as shown on this map by the pale yellow and green colours. And the vast majority of the known mineral deposits, shown by the coloured symbols on the map, have been found in the approximately 20% of the country in which the older rocks actually outcrop. And in these outcropping regions, geological mapping and near-surface methods of detecting mineral deposits have been relatively successful. But this leaves approximately 80% of the continent as a relatively underexplored opportunity for further resource discovery, but leaves us the challenge of how to reduce exploration risk in these covered regions. And this challenge has received significant attention in the Australian geoscience community, leading to this industry roadmap shown here on the right, titled Unlocking Australia's Hidden Potential. This articulates the challenge of exploring through cover and provides priority lists of data types and activities needed to address those challenges. At Geoscience Australia, as a government geoscience agency, our challenge has been, what can we do to demonstrate sufficient resource potential in these covered regions that industry will be encouraged to take up opportunities and actively explore in these covered frontier regions, and ultimately not just to explore but to discover significant new resources. In the two case studies that I present today, we feel we have demonstrated an approach and some success in tackling this challenge. Both the case studies come from Northern Australia, in the region between the towns of Tennant Creek and Mount Isa. Both of these towns exist because of the local mining industry, both historically and ongoing. But in between Tennant Creek and Mount Isa, the terrain looks like these photos on the right. It's flat, featureless, there's not a rock to be seen for hundreds of kilometres, and not surprisingly, the region hasn't seen much resource exploration and very few significant discoveries. But the adjacent regions do contain significant resources, as shown by the coloured dots on the map. In the southwest part of the map area, there are significant small but high-grade gold-copper deposits around the town of Tennant Creek, and these are hosted in Paleoproterozoic iron-rich metasedimentary rocks, and the deposits have been dated at approximately 1850 million years old. Along the northeastern part of the map area is the Carpentaria zinc belt, and this is one of the richest zones of sediment-hosted base metals in the world. And these base metal deposits are hosted in slightly younger but still Paleoproterozoic to early Mesoproterozoic sedimentary rocks, with depositional ages broadly spanning the range from approximately 1800 MA to about 1600 million years. And in the northwestern part of the map area is the Beetaloo Basin, hosting significant shale gas. So for all these reasons, we have every reason to suspect that the central yellow region on this map will host significant resources. But our challenge is how and where do we start in a region as featureless as this, with a size of approximately 300 kilometres wide and about 600 kilometres long. As I mentioned, there is potential for various different mineral and energy systems of interest in this region, and they're all expected to be hosted in slightly different geological settings and have different, geological ingredients. But despite that, our approach has some commonalities in looking to focus attention to specific regions across this massive area. Our approach involves characterising the underlying geology at the broadest scale, primarily with geophysical methods, to identify features of interest, and then to follow up those features with additional, more targeted studies, and then test those features with stratigraphic drilling. So the map on the left summarises the broad geophysical acquisition that we've undertaken across this whole region. There's an extensive series of reflection seismic traverses shown in the bold brown and purple lines. There is regional to sort of semi-continental scale 20 kilometre spaced airborne electromagnetic survey shown by the thin orange lines. There's a grid of approximately 55 kilometre spaced long period magnetotelluric deployments known as OSLAMP shown in the red dots. Similarly, an approximately 55 kilometre spaced passive seismic survey known as OSArray shown by the white dots, and these complement the existing coverage of gravity and magnetic surveys across the region. These data have allowed us to identify geophysical features of interest and then target more focused acquisition, building up geological and resource system hypotheses to then test with stratigraphic drilling. And this approach has led us to two distinct campaigns of stratigraphic drilling for different resources in different parts of the region, as shown on the map on the right. The red polygon outlines the region just to the east of Tennant Creek, imaginatively termed the East Tennant region. And there the mineral system target is broadly an iron oxide copper gold style mineralisation, similar to what is seen at Tennant Creek. And the blue polygon further east outlines the Carrara sub-basin, where the target is both hydrocarbons and sediment-hosted base metals. So turning to the East Tennant region, on the image on the left, we can see in some detail some of the geophysical features that led us to hone in on this particular region. There are a variety of geophysical features that help define a broadly east-northeast trending corridor, and these include near-surface faults shown by the bold black lines that have been interpreted from magnetic data. There's a significant step or gradient in the thickness of the whole lithosphere across this corridor, and that's shown by the dotted contours. So in the north you can see lithospheric thicknesses of over 200 kilometres, and then to the south down to about 175 kilometres. And we also see a zone of enhanced electrical conductivity following this east-northeast trending corridor, and that's been defined by the OSLAMP magnetotelluric survey. And on the right we see crustal scale faults imaged in a reflection seismic traverse across the region. So collectively all these data are pointing us towards a structural corridor that may have the potential to be focusing mineralising fluids in the mantle or deep crust towards near-surface depths. And this structural corridor also is situated along strike from known mineralisation in the Tennant Creek district. So for all these reasons, we felt that this east-northeast trending corridor was an area worthy of further investigation. And there was additional broadband magnetotelluric traverses conducted across it. And after that, a campaign of stratigraphic drilling was designed. The map on the lower left shows the location of the stratigraphic drill holes, and this drilling program was conducted in collaboration with the MinEx CRC as the first of several campaigns within their program called the National Drilling Initiative. There are 10 holes, collectively representing about 4,000 metres of drilling. Those holes were targeted not specifically to intersect mineralisation, but to get a representative samples of the major basement lithologies as predicted from magnetic and gravity interpretations, and to perhaps test for the presence of mineralising fluids along some of the major structures. On the right you see a few examples of some of the core that's come out of this program. There are various types of metasedimentary rocks, magmatic intrusive rocks, variably deformed, and in one case an altered and mineralised drill hole. Typical depth to reach crystalline basement in this campaign was ranged between approximately 100 to 300 metres. So with samples from the drill campaign in hand, an extensive program of analytical work was conducted on those samples, and this has included high-logger hyperspectral scanning, geochemistry, uranium-lead geochronology, argon geochronology, various other isotopic techniques like neodymium and hafnium isotopes. And I won't go through all of those results. Many of them are available on the website. But I guess a key outcome of this work is that the geochronology has enabled us to piece together the stratigraphy and event history of this region in the East Tennant covered area, where previously we were just guessing. And that event history is shown on the right-hand side of the figure here. And you can see a series of sedimentary packages of various ages, episodes of magmatic intrusion shown in the pink, various unconformities and deformation episodes, and then further episodes of sedimentation. We're also now able, with this framework established, to compare that framework with the pre-existing knowledge about the geological history of the Tennant Creek region itself, and that's shown in the slightly to the left. And you can see again a lot of commonality in the stratigraphy and event history between the covered East Tennant region and the outcropping area of Tennant Creek. I mentioned that one of the drill holes was located to test for the presence of fluid alteration and mineralisation adjacent to one of the major structures. And encouragingly, we did intersect altered and mineralised rock in this hole, containing pyrite, chalcopyrite, arsenopyrite and free gold, not at all grades, but sufficient to give us a clear indication that metal-bearing fluids have been transported along some of these structures. And the textural relationships of this alteration and mineralisation with the surrounding host rocks allow us to interpret the timing of this fluid movement at around 1845 million years, the same time as the known gold-copper mineralisation at Tennant Creek. So the upshot of all this work is that we now have a much improved understanding of the basement geology in the region undercover to the east of Tennant Creek. We have robust geochronological constraints on the age and event history of that region, and we have clear indication of mineralising fluids having been focused along at least some of these east-northeast trending structures. So just to give you an indication of the level of improvement, I guess, in the geological map that we have now, on the left is a map that was published in 2020, very much based on interpretation and to some extent guesswork, and on the right the updated map produced after the stratigraphic drilling campaign and the analytical work that has followed. So this provides a clear evidence base for exploration companies to use now to focus their attention in this corridor of interest just to the east of Tennant Creek. I'll turn now to the second case study, further to the east, and this is the area known as the Carrara Sub-Basin. In this case, the initial feature of interest seen in the geophysics was this region of low gravity, shown in the image on the right here, and that was interpreted to be a major sedimentary depot centre, but was untested. You can see on the left-hand image that one of the reflection seismic lines, shown in the orange to brown colours, was located specifically to cross that gravity low to test the interpretation of a depot centre under there. And you can see on the lower right image an interpretation of that seismic line, and indeed the interpretation does appear correct. There is a thick sequence of sediments located on the eastern end of this line below the region with the gravity low, and this is our definition of this area as a newly defined sub-basin known as the Carrara Sub-Basin. It's worth noting that this depot centre is entirely concealed below a younger flat-lying Cambrian basin, the Georgina Basin. So the stratigraphy of this Carrara Sub-Basin is completely untested with any drilling, and that's something that we wanted to address, obviously, with a new stratigraphic drilling campaign. So a deep stratigraphic drill hole known as NDI Carrara 1 was planned for this location shown by the red star here to intersect the western part of the Carrara Sub-Basin. Drilling was completed in December 2020, again with collaboration from the MinEx CRC, and reached a total depth of about 1,750 metres. The upper 630 metres or so of this hole went through the Cambrian Georgina Basin, and below that the lower approximately 1,100 metres were through older unknown Proterozoic stratigraphy. So once again, drilling of a new hole into this untested basin has spawned a very large analytical program. Many of those data and reports are now available on the web page shown in the link. There's not time in this presentation to go through many of those results, but there are a couple of key things to highlight that have come out of that program, and they come from the geochronology of selected intervals and from the organic geochemistry. Uranium-lead zircon geochronology was conducted on key intervals in the holes that were interpreted to be volcanic tuff horizons, and you can see some of the core on the lower left there. Some of these horizons were quite narrow and subtle, but their volcanic origin has been confirmed with thin section analysis where they show beautifully preserved volcanic textures. And this means that collecting uranium-lead zircon ages from these magmatic intervals can give us direct stratigraphic age constraints on the surrounding sediments. This is incredibly useful, and you can see the results shown against the stratigraphic column on the right here. The key things to note here are that several of these tuffs near the bottom of the hole combine together to give an age of around 1,611 million years, and then a couple of intervals further up the hole yield, as expected, slightly younger ages, one at about 1,600 and one at about 1,588 million years. So collectively, these data bracket much of the stratigraphy that was intersected in NDI Carrara 1 to the interval between about 1610 and 1590 million years. So knowing now those age constraints and going back to the seismic sections, we can now correlate confidently rocks from the western part of the Carrara subbasin, where they were intersected in NDI Carrara 1, shown in the little drill hole symbol. We can confidently correlate those rocks with the rocks over 100 kilometres to the east that host the Century zinc mine, and that correlation is shown by the pale green horizon on this image. So the fact that we now have rocks intersected in Carrara 1 of similar age to the hosts to the Century mine has clear implications for possible further base metal potential, and indeed companies have taken up tenements along that western edge of the Carrara sub-basin where those rocks come relatively close to the surface on the basis of this evidence. I also mentioned a program of organic geochemistry, and that was to test the hydrocarbon potential of rocks in this hole, and indeed there are several intervals regarded as having some hydrocarbon potential. Those include intervals both within the overlying Georgina Basin in the interval between about 360 to 425 metres of depth, and in that case the organic geochemistry and total organic carbon contents there are regarded as being an oil-prone interval. Further down in the Proterozoic section there's another interval of elevated total organic carbon between about 680 metres and 725, which is regarded as gas-prone on the basis of its geochemistry. And then further down again, over a wider interval between about 1150 and 1500 metres, there was a sustained release of gas during drilling, showing the gas potential of that interval. So there's clear indications of hydrocarbon potential in this Carrara sub-basin, as well as the sediment-hosted base metal potential that we've talked about previously. So stepping back again to our initial challenge, I guess the question we were trying to address was, can government geoscience demonstrate sufficient resource potential in covered regions to encourage industry and to take up ground and actively explore? And the answer in this region has been clearly yes. The map on the left shows tenement uptake in this region, with mineral tenements shown in green, petroleum tenements shown in blue. There's, as you can see, listed here around 360 tenements and about 38 companies involved. And collectively that represents an area of over 170,000 square kilometres of new tenements taken up in recent time. For our North American audience, that's an area slightly bigger than the size of the state of Florida. And many of those companies are happy to acknowledge that pre-competitive geoscience, government geoscience work that the Exploring for the Future program has collected has been instrumental in them taking up that ground. So there's lots of activity going on there now. There's no major discovery yet, but it's still very early days. As I said, most of these tenements have only been taken up in the last 18 months to 2 years. So we are confident that at least some of that activity should lead to discovery. And stepping back further again to our cover challenge at the Australian scale, I guess what we've talked about today are two case studies from an area in Northern Australia, as shown in this box, where we feel we've been able to demonstrate an approach that has led to increased industry activity and where we are confident that discoveries will follow. So our final key message here is that there is plenty more exploration opportunity undercover in Australia when you look at the map of Australia as a whole. So thank you for listening.